Hi friends, so today we continue with our lecture and today's class I'm going to talk about viscous flow and the boundary layer. So these are very important concepts. This is lecture 15 in our course and I'm Dr. Ranjit Ganguly. Now if we consider frictionless flow, which we have been considering till now, and you think about a flow taking place around a cylinder, for example the cylinder in green shown here, what you will predict is streamlines like this, which I have shown here, and you will essentially predict that there is no drag because of the presence of this cylinder in the flow. And this happens because we are assuming frictionless flow, so the flow is symmetric, and you can clearly see there is going to be no drag here. Now, if we do this experiment in real life, of course, we are going to find that there is drag present here. So how do we solve this contradiction? So essentially, in the beginning days of fluid dynamics, a lot of work on these kind of problems was done by mathematicians and physicists, and they had some doubts about their theories because essentially frictionless flow could not predict drag, could not predict that drag was present in any flow in these kind of bodies. So this paradox was known as the D'Alembert's paradox. Now, what happens in reality is that we have flow separation. So you take a cylinder like this, if you send air on top of this cylinder, you are going to get some regions behind the cylinder where the flow has separated and there are complex flow patterns which are out there. So the symmetry between the front and the back sides of the cylinder is essentially removed. So what you get is you get drag in real flow, and this comes from flow separation, and flow separation is also a result of viscosity. So these are some of the things which essentially lead to drag in real flows, and therefore the paradox was resolved once people figured out viscous flow and flow separation. Now let us start looking at this kind of flow in more detail. So there is a concept known as a boundary layer, and what happens is that if you have an airfoil and we have flow going on top of the airfoil, then if you are pretty far away from the airfoil, you have essentially frictionless flow. However, if you are very close to the airfoil boundaries, then you have a layer where viscous flow takes place, and I have shown this in the red boundary drawn around this airfoil here. So essentially this region is known as the boundary layer, and the boundary layer has a certain thickness. We use the Greek letter delta to show that thickness, and the boundary layer is going from this point A here to the point B. Now of course in this diagram I have shown the boundary layer to be very thick, but actually it is much thinner. We have just shown this for clarity here and to make a drawing. Now what's going to happen is that there is going to be a shear stress present because of the boundary layer and viscosity at the surface of the airfoil, and this is the reason why we get something known as skin friction drag. So the boundary layer concept was introduced by Prandtl, and this explains viscous flow. We already discussed that boundary layer is a region of flow near the surface of the body, and the air velocity changes from zero at the body surface. That means at the point A, the air velocity is zero, and then if you go to this point B, it reaches the value given by frictionless flow at the end of the boundary layer. So now going back to our frictionless model, what frictionless flow would assume is that there would be a streamline, and because there is no friction present, it would essentially slip on top of the airfoil surface very smoothly, and so there would be no drag due to viscous flow and so on. So this model of course we know is not true. So what actually happens is that the slipstream or the flow on top of the boundary layer or just at the border of the boundary layer, this is going to be frictionless. So we can essentially classify the flow into two parts. We can say that inside the boundary layer we have viscous flow, and outside the boundary layer we have frictionless flow. So this essentially lets us use the various equations we have developed before at points which are on the surface or outside the boundary layer. So for example, if I have point 1 and 2 which are on the surface of the boundary layer, then I can invoke the Bernoulli's equation between these 2 points. And remember, this equation has been derived for frictionless flow because the Euler equation assumed frictionless flow, and we can use it at these point 1 and 2. So we can write P1 plus half rho V1 square is P2 plus half rho V2 square, where 1 and 2 subscripts correspond to these two locations. Now, this is a major simplification in fluid dynamics, and it does tell you why all the frictionless flow fluid mechanics which you study is all useful, because all you have to do is that apply those equations to the points which are outside the boundary layer, and inside the boundary layer you have to have some different philosophies going on. So inside the boundary layer you are going to get viscous flow, and the boundary layer again looks like this. This has been shown in an exaggerated form. So the boundary layer has thickness delta. It goes from point A to B. At point A velocity is 0. At point B velocity is V2, which is the velocity corresponding to the frictionless flow value, and the profile of the boundary layer is something like this. So it slowly goes up and it's in the shape of a parabola. So these are things to remember, that frictionless flow is present outside the boundary layer, which I have shown here, and viscous flow is present inside the boundary layer, which I have shown here. And this concept was one of the primary discoveries by Ludwig Prandtl, and this was made in 1904. So now there are some more facts about the boundary layer which have been obtained by experiment. For example, one of the facts is that pressure across the boundary layer is constant. So we can say that PA equals PB. So that's the pressure here, and that's constant throughout the boundary layer, and also that skin friction drag happens due to the boundary layer. So this is given by this tau subscript W. W stands for wall here, and then we can write tau W as mu dv by dy. V is the velocity and y is of course the coordinate axis corresponding to the boundary layer thickness. So essentially this is at y is equal to 0, so that means it would be at the surface. So mu is the absolute viscosity coefficient. This is a property of the gas. So if we are considering air at standard sea level, then mu is equal to 1.789 into 10 to the power minus 5 kg per meter second. So just like we have density of air, we also have viscosity of air as a fundamental property. So now there are two types of viscous flow. These words are often used in common language. For example, you must have heard about laminar flow and turbulent flow. And essentially laminar flow constitutes a situation where the fluid particles which are there move in a smooth and regular manner. And turbulent flow is such that the fluid particles move in a random and irregular manner. Though there is some debate that turbulent flow also has some degree of regularity, which is of course governed by the partial differential equations governing fluid flow. So let's now again look at the boundary layer and look at the differences you would have in the laminar and turbulent flow or boundary layers corresponding to these flows. So if we look at laminar boundary layer, I have drawn that in the red here, red color here. Again, the thickness here is delta laminar. The turbulent boundary layer, the thickness is delta turbulence or subscript turb. So essentially we immediately see that the thickness of the turbulent boundary layer is greater than the thickness of the laminar boundary layer. So this is a fact which takes place, and you can clearly see it in this diagram here. Now, the second thing which happens is that the skin friction drag in the turbulent boundary layer is greater than the skin friction drag in the laminar boundary layer. And this is because the slopes here have this following pattern. So actually the laminar slope at y equal to 0 is less than the turbulent slope at y equal to 0. So let's look at what is dv by dy. So actually most of the time we are used to thinking of dy by dv. We consider the slope in this direction. But dv by ty means you look at the slope again in this direction, but think of this as the y-axis and this as the x-axis. So in that case you can see that the slope here is less. So if you were to draw a line like this, than the slope here. Okay. So you are looking at it from this side. So then you can clearly see that the turbulent boundary layer has a higher slope present here, and so there is going to be a higher value of skin friction present for the turbulent boundary layer. So that's going to make the turbulent boundary layer have more skin friction drag, which may be deleterious for certain situations. For example, if you have an aircraft, typically you want low drag because drag needs to be countered by propulsive force of the engines, and those take power and that consumes fuel, which costs money. So let's summarize whatever we learned in the lecture today. So we saw that frictionless flow, which we have been discussing until now, it completely ignored viscous effects. Real flow has drag due to the presence of viscous effects and also flow separation which takes place. Now the boundary layer has viscous flow and outside flow is frictionless. So this is one of the major conceptual points which was made in fluid mechanics, which let us essentially model the fluid in a much simpler manner. And we also saw that the boundary layer has two types. There is a laminar boundary layer and a turbulent boundary layer. The turbulent boundary layer is thicker, has more drag, and viscosity determines the shear stress. So again, from this equation here, we can clearly see the link between the skin friction drag, the viscosity, and the velocity slope at y equal to 0 or at the surface of the body you are at. So the fact that turbulent boundary layer is thicker and the drag is more will play an important role in the design of airfoils for particular flight conditions. So if you have a specific type of vehicle you are designing, for example, if it's a subsonic transport or if it's a transonic aircraft or it is an aircraft which needs to fly at very high locations, you will have to essentially figure out the boundary layer you want and the boundary layer which is going to be most suitable for you. Now, it's not that turbulent boundary layer is always bad. There are situations where turbulent boundary layer may actually be beneficial that we are going to discuss later in this class. So that was the lecture for today. So we got introduced to the concept of viscosity and the boundary layer. These are extremely important concepts in fluid mechanics and of course within the aerospace engineering domain. I will end this lecture now. I will see you in a video sometime soon. See you then.